In this lecture, I want to add another symbol to the stock of symbols that we have in predicate logic, a symbol that will allow us to represent sentences expressing claims about identity. So consider the following sentence. Clark Kent is identical to Superman. This is a sentence that we would like to be able to represent in our language. So we can get started on that as follows. We can let K abbreviate the name Clark Kent and let S abbreviate the name Superman. And now we're also going to introduce a new symbol into our language, the equals symbol. And this symbol will stand for is identical to. Okay, now that we have this symbol in our language, we can go ahead and translate the sentence Clark Kent is identical to Superman as follows. K equals S. Okay, that's all relatively straightforward. But now that we've introduced a new symbol in our language, we need a couple of rules to govern that symbol. So we're going to introduce an identity introduction rule and then an identity elimination rule so that we can make inferences involving the identity symbol. So let's begin with the identity introduction rule. So consider the following sentence. N equals N. This sentence is a good candidate for expressing a logical truth. It seems as though it's true as a matter of logic, for example, that Socrates is identical to Socrates, or that Professor Boyce is identical to Professor Boyce. These seem like good candidates for logical truths. Now, there are actually some philosophical problems with taking sentences like these to express logical truths, and we'll consider some of those problems a little bit later on in the course. But for now, let's go ahead and take it for granted that we do want these sentences to come out as logical truths. Well, if we want the sentence N equals N to come out as a logical truth, then we want it to be a theorem. That is, we want the following sequence to be valid. Turnstile N equals N. That is, we want the sentence N equals N to follow from no premises or from any premises. And the rule of identity introduction does this. The rule of identity introduction makes the sentence N equals N a theorem. So here's the rule stated. One may always write down a line containing a sentence of the form N equals N, where N stands in for an arbitrary or non-arbitrary name. That's it. That's the rule stated. Let's go ahead and look at a simple example of the rule applied. So here is the sequence that I just said we wanted to be able to prove in our system. And the rule of identity introduction allows us to do this in a very straightforward way. The proof of this sequence requires only one line. We just write down N equals N, and what justifies us in doing that is the rule of identity introduction. And that completes that proof. Okay, let's look at a slightly more complicated example. Consider this sentence. For any x, there exists a y such that x equals y. That is, anything is such that it is identical to something. Okay, we may begin this proof as follows. First, we can write down the sentence A equals A. We're justified in doing that by the rule of identity introduction. We're just allowed to write down a sentence of the form N equals N using any name we like, an arbitrary or a non-arbitrary name. So I just write down such a sentence of that form, A equals A, using the arbitrary name A. Okay, now that I've done that, I need to get a sentence involving quantifiers. So here's the first thing that I'm going to do, I'm going to go ahead and apply the rule of existential introduction. But instead of replacing both occurrences of A with the variable y, I'm only going to replace one occurrence of that variable, one occurrence of the name A with the variable y. So you see that I've done that on line 2. I've taken the right occurrence of the name A and replaced it with the variable y, and then I've added the existential quantifier. The rule of existential introduction does permit me to do this. The rule of introduction doesn't say that I have to replace all occurrences of the name in question with a variable. I can just replace some of them with the variable if I wish. So that's what I've done. Okay, now that I have this sentence involving the arbitrary name A, I'm now in a position to apply universal introduction to what occurs on line 2 to get my desired conclusion. And that's it. This proof is pretty straightforward, but it involves some moves that so far might not be familiar to you, so you might want to pause for a moment and take in just exactly what was done in this proof. Study this proof just a little bit. Okay, moving on to the next rule, the rule of identity elimination. So consider the following argument. Mark Twain is identical to Samuel Clemens. Mark Twain is an author. Therefore, Samuel Clemens is an author. I think that this inference is straightforwardly valid. If we represent it in our notation, it comes out as follows. M equals S, AM, therefore AS. Alright, the rule of identity elimination allows us to prove that this argument is valid. So here is a statement of the rule. Suppose one has a line that contains a sentence of the form m equals n, where m and n stand in for arbitrary or non-arbitrary names. Then given any line that contains the name that corresponds to m, one may write down a new line that is exactly like it, except for the fact that one or more occurrences of m are replaced by an occurrence of n. Well, that's a bit of a mouthful, but the rule itself is actually pretty straightforward. Let's go ahead and look at an example. So here's the sequence that we just introduced. We begin, of course, by writing down our premises. Now we use the rule of identity elimination applied to lines 1 and 2 to get the sentence AS. We can do that because line 1 tells us that M equals S, and on line 2 we have AM, and the rule of identity elimination tells us that since we have the sentence M equals S, we can take any sentence that involves an occurrence of the name A and replace one or more occurrences of the name M in that sentence with the name S. So that's what we've done here. We've taken the name M that occurs in the sentence on line 2 and replaced it with the name S. That's it. A relatively straightforward example of that rule. Okay, now that we've introduced the identity symbol and introduced a couple of rules that govern that symbol, I want to talk about some of the formal properties that identity has. First of all, identity is reflexive. That is, everything is identical to itself. For any x, x equals x. That's how we represent formally the fact that identity is reflexive, that everything is identical to itself. Identity is also transitive. That is, for any x, any y, and any z, if x equals y and y equals z, then x equals z. Identity is transitive. And finally, identity is symmetric. That is, for any x and any y, if x equals y, then y equals x. So these are important formal properties of identity. In fact, any relation that has all three of these properties, any relation that is reflexive, transitive, and symmetric, is what logicians and mathematicians refer to as an equivalence relation. And identity is an equivalence relation. It is a paradigmatic example of an equivalence relation. Okay, so now that we've identified these formal properties of identity, I'll go ahead and give you an opportunity to prove, using the rules that I've just given you, that all of these sentences are theorems. And that is your current homework assignment.